fundamental theorem of calculus. And the fundamental theorem of calculus, as you can tell by its name, is a pretty important theorem of calculus. Okay, so I am not going to go through like a full proof of the fundamental theorem of calculus. I'm going to just give you guys an idea, particularly since we just went through that big, long, confusing thing, right? The fundamental theorem of calculus is really where calculus sort of came together as one, like, big unit of study of mathematics. Because so far, we have looked at two different questions. We have spent a lot of time talking about derivatives, right? Derivatives are the slope of your tangent line, right? Derivative gives you slope of a tangent line at any point. And there were a lot of mathematicians that were doing work with slopes of tangent lines. So I've listed several here. Isaac Barrow, René Descartes, Pierre de Fermat, I think is how you say that, Blaise Pascal, John Wallis. All of these mathematicians were doing work with finding the slope of tangent lines for different functions. I don't know in particular exactly what they were doing, but they tell me they were working on this stuff, right? There were other mathematicians that were working on integrals, finding the area underneath the curve. That's what we've been working on so far. Riemann's not in that list, but I feel like Riemann maybe should be there, because he definitely was thinking about area under the curve with those approximations. You will also notice that there are a couple here that are in both lists. Isaac Barrow and Fermat, I didn't put his full name on that second one, but those are both working in both branches. However, none of these are attributed with discovering calculus or creating calculus, whichever way you want to think about it. I don't know if I've talked about this earlier, like in pre-cal with you guys, but who generally came up with calculus? You guys know? Isaac Newton. Anybody know anybody else? Isaac Newton is generally who people will say created calculus. However, this is a very interesting. I've read a whole book on this. It's fascinating. I read a book a while back called The Calculus Wars. So Isaac Newton is generally credited with coming up with calculus. He was an English mathematician in the 1600s that is generally credited with coming up with calculus. However, there was also a German mathematician named Gottfried Leibniz. And Leibniz also was coming up with calculus pretty much at the same time as Newton. So, Newton actually had discovered calculus long before he published anything. And the reason that Newton and Leibniz are credited with coming up with calculus is not because they learned how to take a derivative or because they learned how to take an integral. What Newton and Leibniz discovered is that derivatives and integrals are inverses of each other. So finding the slope of a tangent line is the inverse of area under the curve. Like those two ideas are inverses of each other. So to undo an integral, you can take a derivative. Or to undo a derivative, you can take an integral. That was the huge idea. So they were already doing some work on these, and they discovered that these two things were inverses. And then they developed a lot of different rules and notation and different things for this. But Newton had done some earlier work, because Newton is very famous for lots of different things, not just mathematics and not just calculus. But he had done a lot of work, and he had published a paper, and I cannot remember what it was on. But Newton had published a paper on something, and a few years after he published it, he was wrong. And so, other mathematicians said, hey, this part right here, you messed it up, and they published that, and they were so it was publicly known that he was incorrect. And Newton did not take that well. He did not like the world knowing he was wrong, and he was wrong on that, whatever, I can't remember what subject it was on. So Newton had decided that he was basically going to do all this math and all this work, and he was going to keep it to himself. And maybe he would leave his papers behind to be published when he was dead, but he couldn't even fathom the idea of going through that again, of people criticizing his work. So probably what happened is he probably had discovered calculus before Gottfried Leibniz. However, Leibniz did not have the same, avoidance of publication. So Leibniz also discovered calculus and published his work first. Well, whenever Newton saw that Leibniz had published work on calculus, Newton was like, Leibniz has stole my work. That's what I was doing. And so then Newton is mad at Leibniz, and Newton did end up publishing his work because he's accusing Leibniz of stealing his. So he's like, well, I guess I'm going to have to get over it and actually publish this. And so Newton published his work after Leibniz had published his. Leibniz then accused Newton of stealing his work because he had already published his stuff, and then Newton's like, oh yeah, I had this too. So both men accused the other of stealing their work and hated each other till their deaths. I would say that it was resolved because there was a Royal Society that was just this group of brilliant minds of the time that met and discussed and would send each other letters and papers and stuff to look over. In the book that I read, it would list several of those, and there would be names I recognized, like Bernoulli. There, I was like, oh yeah, I remember that from science class. I remember exactly what it was, but I remember there was a Bernoulli's principle. It was what was that, pressure? I can't remember. Anyway, I heard the name, right? The Royal Society did do an investigation into who was the rightful father of calculus. And the Royal Society at the time determined that Isaac Newton was the father of calculus. However, guess who was the president of the Royal Society at the time that they made this decision? Isaac Newton. So, the book that I read, its opinion on the matter was that there was already a lot of work done, both with derivatives and integrals. So it almost was inevitable that some genius was going to put all this together. As you see, Isaac Barrow and Fermat both were in the running to come up with this idea because they were both doing some work on both of these ideas. Had it went on a little longer, or they were born a little later, maybe they would have came up with it. But it was almost inevitable somebody was going to come up with it. The book generally had the opinion that both men probably discovered calculus on their figured it out on their own and published at separate times, and nobody actually stole the other one's work. It was just sort of going to happen that somebody discovered this idea. So, it was a really, like, the writer of that book did a really good job of, like, kind of making it interesting, even though, I mean, there were definitely some boring parts where they get into some stuff, but, like, giving you sort of the background on who they were and what they did in their lives and why Isaac Newton didn't just go ahead and publish as soon as he figured it out. We actually, most of the notation that we use in, like, modern day calculus is more based on Leibniz's notation. Newton's notation was, like, a little clunkier and harder to deal with, and although he's doing the same thing, we generally don't use his notation as much. I don't think I put this on here. See if this comes up well. Oh, yeah. This is a picture. This is still in existence. I want to go there. So, if I get to go to England anytime soon, it's on my list. It's on. Stupid stuff coming up. This is a picture of Newton's, like, home he grew up in. You can go visit it, and look at these symbols on his house. This is fascinating to me. They look like integral symbols, but those are just braces that they would use to keep, like, floors from shifting. Because, I mean, this is obviously it's still standing. It's a very, very old house. I think they said that they would have been on the house, though, whenever he was alive. But they're just like braces of some sort that are put on the house. And Newton actually never used that symbol. Leibniz used the integral symbol like that. But the integral symbol was just, like, right there on his house all of his life growing up. And I think, like, if you go visit this, it was like a calculus training I was at. One of the teachers had been there to visit, and he said, like, he did most of his experiments in, like, this one, like, room in this house. This is where he, like, he's a genius. I guess it's like the movies. He's just kind of, like, holed up. Probably didn't have a lot of, like, social life so much. Just, like, studying things and experimenting and all that. And you can, like, go into that room. And the guy that was telling us about it, that was doing the calculus training, he said that he went in that one room and spent 4 hours in the one room, just, like, looking at different things and thinking about the experiments he'd done. And anyway, he made me really want to go see this. I don't know if the rest of my family is going to care about it quite as much as I do, but and I don't know that I'm going to spend 4 hours in the room. But I will probably spend longer than the average person. This is kind of neat. I wanted to go see, we went to Germany a couple years ago, and I wanted to go see, like, some Leibniz stuff, but most anything dealing with Leibniz was destroyed in World War II. So there are a couple things. There's, like, a monument, and there's, like, a building that they rebuilt that, like, has his name on it, but, like, it's not the original building. It was rebuilt later. And it was also, like, way up further north than the other places that we went, so we did not go. If there was more, like, original stuff, I may have drugged my whole family to that, too. But there wasn't. So there's a little math history, which I think is really, it's just mind-blowing to me. Like, I love, like, learning calculus. I can think of, like, how, oh, yeah, this all makes sense. But, like, to think of coming up with all these ideas. Like, because all of that stuff that I just did, like, they didn't just, like, have somebody show them how to find an integral, right? Like, they decided, oh, we could use summation notation. Like, somebody developed summation notation. And then somebody developed these special rules for it. And then somebody was like, oh, we could use that here for these rectangles. And then if we do the limit as n approaches infinity, oh, that's the exact area. Like, they were coming up with these ideas on their own. Ideas that a lot of times, especially when, like, that stuff right there, I had to go look back at my notes to make sure I was going to do it right for you guys. Like, I'm barely holding on when somebody shows me how to do that. To, like, think of being the one to come up with all of that is, like, pretty fascinating to me. Now, if I'd been, like, if I could live in ancient times, I'm sure, like, I would not have came up with calculus. I'm also a woman, so I probably would not have been allowed to learn anything. But, like, if you go back far enough, and I somehow dealt with a lot of triangles, I think the Pythagorean theorem was not out of my reach, you know, like, oh, wait, this always seems to have this relationship, you know. That, like, I can see where someone came up with some of that stuff. This stuff, I mean, like, mind-blowing. And then to think that there are, like, actually, like, mathematicians coming up with, like, new stuff today is crazy. Like, feels like we should already know everything there is to know. But, so, now, the stuff that mathematicians are coming up with today is stuff like I don't really even hardly understand what they're doing. And I have a 4-year degree in straight math, not even math education. And so, like, the likelihood that new math is going to, like, show up in everyday stuff, very, very, very low. You know, it's not. A lot of new math is, like, they're just doing math to do math. They don't even know if it's going to be useful one day. They're just, like, they, like, want to figure out if there's a formula for coming up with the next prime number or something like that. It may or may not exist, and it may or may not be helpful once they figure out what it is, if it does exist. And so, but there have been a lot of things that mathematicians did in the past. Like, I don't have concrete examples of this because it's all a little above where I'm at, but, like, but I've read several. I love to read, like, math books that show you, like, where higher level math stuff is applied. And I can't remember, like, the specific example, but one book I was reading was saying, like, there's a lot of things that mathematicians learned, like, they figured out just for the sake of math, right? Like, but it has ended up being very helpful in different areas as, like, computers advance and stuff. Like, I think, for example, like, imaginary numbers have a lot of applications that the original users of imaginary numbers had no idea would, like, come into play. So, anyway, there's our history lesson. That has taken us too long. That's okay. All right, so the actual work for this is actually pretty easy. Okay, so fundamental theorem of calculus connects integration and differentiation. So far, we know that the derivative is the slope of a tangent line, and the integral is the area under a curve. Right? The fundamental theorem of calculus says if f is a continuous function on the interval containing a and x, then this right here is our fundamental theorem of calculus. If we take this notation right here, means take the derivative. If we take the derivative of something that was an integral, then we just get the thing that we were taking the derivative of, right? They undo each other. Take a derivative of an integral, they undo each other. Now, there is one thing we have to watch out for. Notice right here, we've got an x, and right here we had an f of t, and then the switch to an x right here. Okay, so we'll talk about, like, what's happening in that case. So let's just do some problems. So right now, we'll be doing problems where we're taking a derivative of an integral. All right, and we're not learning how to like integrate or anything yet. We're just learning that derivatives and integrals undo each other. All right, so in order for this to happen, there's a few things that have to be the case. First of all, this lower limit must be a constant. So it has to be a number. It can be a letter as long as they tell you somewhere that letter is a constant. Okay. So if I'm taking the derivative of an integral and this lower limit is a number, then all we're going to do is take whatever is right here. We're going to plug it in for the variable like this. So we'll get x squared minus 4x. And then we do have to do almost like a little chain rule right here because we're taking the derivative. And we're going to multiply that by the derivative of whatever is right here, which is our x. But what is the derivative of x? It is just 1. So we get x squared minus 4x. They use a different variable here. This is sort of like a placeholder or a dummy variable. So they're using like a t here. Like this x right here should never match whatever letters on the inside of the function. But it does get replaced in. It cancels itself out is what happens when we learn how to like actually do this with numbers. We'll see why. But it sort of cancels itself out. So nothing. It doesn't matter whether that's a 2, a 7, a 15, a 0. It could be an a as long as they're telling you a is a constant. It doesn't change the problem at all. Now, if you have a variable there, if you have like an x to an x squared, changes the problem entirely. We'll have to know something else before we can do that. But you won't see that today. So see here, we've got a number. All we're going to do is take this right here, take the x, plug it in for the variable. We know the variable is the k because we see dk over here on the end. And we will get e to the x plus 4. We will multiply that by the derivative of x, but what is the derivative of x? Just 1. So we're done. That's our answer. Okay, let's look at what happens whenever we have an expression that's not just the x up here. So in this case right here, a, we'll make ourselves a note, a is a constant. And so if we are going to take the derivative of an integral from a to g of x being some function here, it could be x squared, it could be 2x minus 4, it could be something really complicated, whatever this is. We're going to do the same thing we were doing on the last problem, but this time we got to plug in g of x where the variable is, right there for the t. So we'll have f of g of x, and then we must multiply that by the derivative of g of x. On the other problems that we just did, that derivative was 1, so we didn't have to do anything, but here we'd have g prime of x. And you'll notice that looks a lot like our chain rule, right? So let's look at application right here. The number here on the bottom does not matter what number it is as long as it's a number. If it's a variable, I've given you a problem you can't do yet. Right there. So we are just taking the x squared. We're plugging it in everywhere that we have an a. So we will have x squared minus x squared squared over 4x squared. So all of those a's get replaced with the x squared. The dA is telling you what variable you're taking the integral with respect to. It just drops. You don't put, whenever you differentiate the integral, it cancels each other out there. And then we must multiply by the derivative of the x squared, which would be 2x. So that's sort of like the little chain rule piece to it. So for this, you would just probably simplify here. So you're going to have x squared minus x to the fourth. I'm going to cancel this x right here with one of the x's in the bottom. I'm going to also reduce this 2 and this 4, which will just give me a 2 here in the bottom. So we got x squared minus x to the fourth over 2x. You may also see them do this where we would just have like x to the first power minus x to the third over 2, because that we could like factor out an x and cancel it with that one in the bottom. Okay, here, let's try to do at least one more. So like if I have example 4, I'm going to take this right here, I'm going to plug it in. So I'm going to get 8 square root of x squared minus 4. And then I've got to multiply this by the derivative of x squared. Remember, x squared is the same as x to the 1/2. So that'll be 1/2 x to the negative 1/2. Your assignment tonight is going to be on delta math. I can't remember how far they make you go, like simplifying here. Definitely a square root and a square cancel each other out. You're going to have 8x minus 4 times, I would write this as 1 over 2 square root of x. So I'd probably write my final answer as 8x minus 4 over 2 square root of x. And so like if I do this, this one here, I'm taking the derivative of an integral. I'm just going to plug in. I'll get x squared minus 3x plus 1 to the third power. And then I'll multiply by the derivative of x squared minus 3. So that'll be 2x minus 3. They probably wouldn't simplify that any further. Okay, we're not getting into the applications quite yet, but that is okay. Because your delta math doesn't really have those on there either. It's just the mechanics of doing what we did on those first ones.